For all our incredible medical technology, we still struggle to keep a donated organ viable for more than just a few hours. It's a race against the clock. Meanwhile, nature has completely mastered the art of hitting the pause button on life itself. We're not talking hours or days, but millennia. Here's what most people don't realize. It's a technology we're only just beginning to copy, and the original blueprint isn't in our labs. It's buried deep in the frozen past.
31,800 years. Just let that number sink in. That isn't the age of a fossil or some ancient rock. No, that is the age of a living thing that scientists recently brought back to life after it was dug out of the Siberian permafrost. And what's absolutely fascinating is how they did it. This wasn't some miracle seed they found. In fact, the ancient seeds they found were completely unviable. Instead, scientists used a tiny piece of fruit tissue they discovered in a fossilized squirrel burrow 125 feet below the ice. And from that one little piece of ancient tissue, they grew a complete, healthy, flowering plant. So this raises a huge question, right? How is that even possible? I mean, common sense would tell you that it must have been just perfectly frozen. But as it turns out, that is the single worst possible answer. Simply freezing something is one of the most destructive things you can do to it at a cellular level. Okay, so to really get this, we have to look at what actually happens on a microscopic scale when water turns into ice. It's not this gentle, peaceful process we imagine. It's actually incredibly violent, and for a living cell, it is an absolute nightmare. And this isn't some brand new discovery. Scientists have known this for a very long time. Way back in 1937, the cryobiologist Basile Huviet figured this out, basically concluding that ice itself is the #1 enemy of preservation for any complex biology. So the key takeaway is this: to survive, you have to avoid making ice in the first place. And here's why. On the left, you've got your standard freezing. Water molecules line up and organize themselves into these sharp, rigid crystals. They act like millions of microscopic daggers, literally piercing cell membranes and shredding all the delicate machinery inside. But look at the right. That's a totally different process: vitrification. Instead of crystals, it forms this smooth, stable, glass-like solid that just locks everything in place without causing any of that damage. So, if ice is the big bad enemy, how do you actually get to that ice-free state? Well, scientists have developed a pretty remarkable technique to do just that. They figured out how to create what's essentially a biological glasshouse for living cells. Vitrification. The word literally means to turn into glass. The whole goal is to cool the water inside a cell so incredibly fast that the molecules simply don't have time to line up and form crystals. They just stop. The liquid's totally random molecular arrangement gets locked solid. It's like a liquid that's been put into molecular stasis. So here's the modern lab recipe. First, you gently soak the cells in these special molecules called cryoprotectants. Think of them as molecular cushions. They replace some of the water, and they physically get in the way, blocking ice crystals from ever starting. Then you cool the sample with extreme speed, and the whole system just solidifies into that perfectly protective, glassy state. Now, this all sounds like incredibly advanced, futuristic science fiction stuff. But this is where things get really, really interesting. Turns out, nature figured all of this out a very, very long time ago, and it put this technology inside some of the toughest organisms you can possibly imagine.
Everybody, meet the tardigrade. You might know it as the water bear. This little microscopic animal is, without a doubt, the undisputed champion of survival on planet Earth. It can enter this state of extreme suspended animation called cryptobiosis, where its metabolism slows down to almost nothing. We're talking less than 1/100th of 1% of its normal rate.
And just look at what that allows it to do. I mean, this is just mind-bending. In their cryptobiotic state, tardigrades can survive the raw vacuum and lethal radiation of outer space. They can be frozen to near absolute zero or boiled well above water's boiling point. They can withstand pressures 6 times what you'd find at the bottom of the ocean and radiation doses that would kill a human 1,000 times over. It's almost unbelievable. So cryptobiosis is basically nature's ultimate pause button. When conditions get really bad, whether it's extreme cold, total dehydration, lack of oxygen, all measurable life processes just stop. The organism isn't dead, not by a long shot. It's just waiting for things to get better. Okay, so we have this ancient plant that can sleep for 30,000 years, and we have this nearly indestructible little animal. They can both just pause life. So how are they doing it? Well, the answer lies in a shared molecular secret, a kind of biological superpower they both possess.
So what is the common thread here? What's the secret weapon? The molecular machinery that connects a plant frozen since the last ice age with a microscopic animal that can literally survive in space. This one detail, well, it changes everything.
The answer is a very special class of molecules called late embryogenesis abundant proteins, or LEA proteins for short. Now, the key phrase you need to know here is intrinsically disordered. It means that unlike most proteins that have a fixed, rigid shape, these are naturally flexible, dynamic, and kind of flocky. So when a cell is full of water and everything's going great, these LEA proteins just kind of float around, totally unstructured and random. You can imagine them like strands of cooked spaghetti just floating in a pot of water. They don't really seem to be doing much of anything at all. But their superpower activates the moment the water starts to disappear. As the cell dries out, these proteins suddenly fold into very stable structures. They link up and form a protective, glassy matrix, a kind of molecular shield that physically encases all the other fragile proteins and membranes, protecting them from damage. They are, essentially, creating natural vitrification inside the cell. And this, right here, is the big revelation. That 30,000-year-old plant, it used LEA proteins to turn its cells into glass and just wait out an entire ice age. The tardigrade, it uses them to survive the vacuum of space. And our most advanced cryopreservation labs, they're basically just trying to copy the exact same process. It's all the same biological software. The fundamental principle is beat destruction by becoming glass.
So understanding nature's blueprint for suspended animation, it isn't just a cool piece of biology. This has absolutely profound implications for the future of medicine, for conservation, and maybe even for human exploration.
I mean, the whole concept sounds like it's straight out of science fiction, but it's a scientific reality. As this quote from the National Institutes of Health confirms, we now have the ability to effectively halt biological time. We can pause the process of decay, of aging for cells, for tissues, and potentially one day for entire organs. And just think about the applications. It's staggering. Imagine organ banks where we could store hearts or kidneys indefinitely, completely eliminating transplant waitlists. This is the exact technology that's crucial for de-extinction projects, like the ones trying to bring back the woolly mammoth. It could help us perfect seed storage for global food security, create vaccines that are stable at any temperature, and yeah, maybe, just maybe, one day enable suspended animation for long trips to other planets.
You know, this whole journey started with a tiny flower that took a 30,000-year nap. And now, by learning its secrets, we're standing on the verge of a revolution in how we control life itself. It really leaves you wondering, if the fundamental clock of biology can be paused and restarted, what other rules are we about to change?
Don't go anywhere, hit subscribe, and we continue.
When you think of flight, you probably think of noise, right? The deafening roar of a jet engine, the whine of a propeller, the annoying buzz of a drone. Our machines just can't seem to move through the air without announcing themselves. But in nature, the perfect hunter figured out how to erase sound itself, to move through the sky like a ghost. So how in the world does it do that? Well, let's find out. Meet the owl. Now, this isn't just another bird of prey, it's an absolute acoustic masterpiece. You see, unlike pretty much any other bird, the owl's entire hunting strategy depends on one mind-blowing advantage: becoming completely invisible to sound. This gives its prey absolutely zero warning that it's coming. So that's the billion-dollar question, isn't it? How did evolution crack a physics problem that some of our best and brightest engineers are still wrestling with today? Well, it turns out the answer has been hiding in plain sight this whole time, literally woven into the fabric of its feathers. Okay, so to solve this mystery, we're gonna have to get up close and personal. We need to look at the clues. And the best part is, they're not buried in some ancient fossil. They are right there in the complex, brilliant, and honestly genius structure of an owl's wing. And here they are, the owl's 3 secret weapons for silent flight, all perfectly engineered into just a single feather. Now, these aren't just random quirks of evolution. This is a fully integrated system, a kind of natural stealth technology. So first up on the list are these things called leading edge serrations. Picture a tiny, fine-tooth comb running along the very front of the wing. It's the first thing that slices through the air. This is piece number 1 of our puzzle. Next, we've got this incredible velvet-like surface. If you could touch the top of an owl's wing, it wouldn't be smooth and sleek. It's covered in this soft, downy texture. It feels like velvet, sure, but its real job is way more important. It's basically a sonic cushion. And finally, we have the trailing edge fringes. Now, where a normal bird's feather has a pretty sharp, clean edge, the owl's looks almost frayed and worn out. But that's not damage. Oh no, that is a highly sophisticated design for controlling how the air leaves the wing. All right, so we've got the what, those 3 key features. Now it's time to get into the how. Let's dive into the amazing physics that makes this natural stealth technology actually work. You know the sound a wing makes when it cuts through the air? It's all about chaos. It's about turbulence. As air flows over any surface, it tumbles and rolls off the back edge in these big, messy swirls called vortices. And those chaotic vortices, that's the noise. That's the sound of flight. And here's where the magic starts. Those serrations on the leading edge, they're like a filter for the air. They grab that big, turbulent rush of air and instantly break it up into tons of tiny, organized, and much, much quieter little swirls. We call them microeddies. It's kind of like taking one loud, crashing wave and shattering it into 1,000 silent ripples. And what about that soft, velvety layer on top? Well, that's not just for looks. This porous, downy canopy acts like a thick carpet for the airflow. It absorbs and dampens all the little pressure changes happening on the surface, essentially muffling the sound at its source before it even gets a chance to become a noise we can hear. And this last part is absolutely crucial. As experts like Justin Jaworski from Lehigh University have pointed out, the back edge of a wing is usually the biggest source of noise. This is where the owl's final trick comes into play. That soft, fringed edge allows the air flowing over the top and the air flowing under the bottom to mix together gently and gradually. It equalizes the pressure and basically diffuses the sound just as it's leaving the wing. So for millions of years, this was just a stunning masterpiece of biology. But now, it's becoming the blueprint for a technological revolution. This is the moment where things get really interesting. Researchers looked at this perfect silent system and asked a really simple question. Hey, what if we could copy that? What if we could give our own noisy machines the owl's gift of silence? And that question led to this idea of aerofeathers. Using incredibly detailed scans and advanced 3D printing, engineering teams started building artificial wings, airfoils, that directly copied the owl's design. The serrations, that velvety surface, the fringed edge, the whole shebang. The goal was to finally bring nature's silence into our world of technology. So did it work? Oh yeah, the results were staggering. By adding a 3D printed attachment inspired by the owl's wing to wind turbine blades, they cut the noise by 10 decibels. Now that number might not sound huge, but to the human ear, that's like cutting the loudness you perceive in half. It's a massive deal for making clean energy quieter. But here's the kicker. It turns out the owl's design isn't just quiet, it's also ridiculously efficient. In tests on drones, just adding those serrations to the front of the wings increased the maximum lift coefficient by a whopping 33.6%. That's basically a measure of the wing's raw power to lift itself up. And it gets even better. That same design boosted the overall aerodynamic efficiency, what's called the lift-to-drag ratio, by 29.5%. This is like the holy grail for engineers. It means more performance, longer flight times, and using way less energy. I mean, just look at this chart. It really puts it all into perspective. You can see the standard drone's efficiency right next to the one with the owl-inspired serrations. We're not talking about a tiny little tweak here. This is a fundamental leap forward in performance. And it's all thanks to an idea that nature perfected millions of years ago. So, what does this all actually mean for us, for our future? Well, this isn't just some cool science fair project. It's a genuine peek into a world that's a whole lot quieter and a whole lot more efficient. The possibilities here are practically endless. Just imagine wind turbines that can be placed closer to our cities without being a nuisance, delivery drones that don't have that irritating buzz, computer fans that are completely silent, maybe even quieter airplanes, and everyday things like vacuum cleaners. This is the incredible potential of looking to nature for answers. You know, when you boil it all down, it comes back to one simple truth. We spend billions of dollars on research and development, but nature has been running the most sophisticated R&D lab on the planet for hundreds of millions of years. The solutions to some of our biggest engineering challenges are already out there, just waiting for us to notice. It really makes you wonder, doesn't it? The secret to next-level aerodynamics was hiding on a bird's wing the entire time? What other incredible breakthroughs are disguised as a simple leaf, or a seashell, or a fish's fin? What else is nature just waiting to teach us?
Don't go anywhere, hit subscribe, and we continue.
When you think of advanced engineering, you probably picture a sterile lab, maybe some billion-dollar factory. But here's what most people don't realize. Some of the planet's most sophisticated material science is happening inside a slow-moving sea creature. It's building a tool at room temperature that can literally grind solid rock and outperform some of our best industrial materials. The question is, how on earth does it do it?
Just let that sink in for a second. We spend a fortune on giant furnaces and high-pressure labs to create our most advanced materials, and nature has been quietly outdoing us in the ocean the whole time. This quote from Professor David Cassilis says it all. We're not just talking about something that's a little bit strong. No, we're talking about a material that's in a completely different class.
And this is the engineer responsible. Say hello to the chitin. It's a marine mollusk that, let's be honest, looks more like a living stone than some kind of tech genius. It spends its days just crawling along, scraping algae off rocks. And to do that, it uses a specialized tongue covered in teeth so incredibly hard they grind away the actual rock without even breaking a sweat.
So, that's the central mystery, right? How does this seemingly simple organism, without any of the fire and pressure we use, manufacture a tool that our best engineers would kill to create? The answer, it turns out, isn't just in what the teeth are made of. The real secret is how they're made.
It all comes down to one of the most efficient and, frankly, elegant manufacturing systems you'll find anywhere in nature. Think of it like a biological assembly line, a perfect little factory that builds these incredible tools from scratch, over and over again, continuously.
The chitin's feeding tool is called the radula, and the best way to think about it is like a conveyor belt, but for teeth. It's a ribbon-like tongue with over 70 rows of these teeth. As the ones at the front get worn down from constantly scraping rocks, new, perfectly sharp teeth are always moving up from the back to replace them. It's a system of perpetual self-renewal. It's brilliant.
And this is what's so incredible. When you look at a single radula, you can see every single stage of tooth development all at once. It starts at the back with these soft, transparent little nubs, and then row by row they get harder and darker until you get to the fully mineralized, jet black, rock-grinding teeth at the front. It's the entire factory floor, from start to finish, captured in one biological snapshot.
So how does this assembly line actually work? Well, it breaks down into 4 basic steps. First, the chitin builds a soft little scaffold out of chitin. That's the same tough stuff you find in insect shells. Then, step 2, it deposits an iron precursor molecule which gives the growing teeth this reddish-brown color. Next comes the magic trick. That precursor transforms into magnetite, the super-hard magnetic mineral that turns the teeth black. Finally, the finished product moves to the front of the line, ready for duty.
Okay, so we've seen the factory. Now let's look under the hood at the molecular recipe. What are the specific biological ingredients that make this incredible feat of nanoscale engineering even possible? And this is where the story gets really interesting.
All right, so here are the key players in this operation. You've got the chitin scaffold, which provides the basic structure. You have a protein called ferritin, which acts like a tiny delivery truck, bringing in all the raw iron. Then you've got the end product, magnetite, the super mineral. There's even a shock-absorbing mineral in the base for flexibility, but the real star of the show, the architect of this whole operation, is a protein they only recently discovered called RTMP1.
And, you know, this detail changes everything. This isn't just a random dump of minerals onto a scaffold. We are talking about a highly controlled molecular assembly process. That newly identified protein, RTMP1, is basically the foreman on this biological job site, telling every single iron atom exactly where to go and how to crystallize with mind-boggling precision.
And here's how it's done. Proteins like that RTMP1 are delivered through these tiny, nanoscopic channels directly to the tooth. They bind to the chitin scaffold, creating a perfect template.
Then, as the iron arrives, delivered by ferritin, RTMP1 directs it to form these perfectly aligned nanorods of magnetite. It is this incredibly precise architecture that gives the tooth its unbelievable strength and hardness.
Okay, so a rock-eating sea mollusk with super teeth, why should we care? Because this humble little creature holds a blueprint for a potential revolution in materials science and how we make things. It's a perfect example of how nature can inspire some serious real-world innovation.
There's a name for this whole concept. It's called biomimicry, and the idea is actually pretty simple. Instead of trying to reinvent the wheel for every single problem, why not look to nature? It's been running an R&D lab for billions of years, and it's already found some unbelievably elegant solutions.
And I mean, just look at this comparison. To make industrial-grade magnetite, we use massive amounts of energy. We're talking extreme temperatures, high pressure. It's a brute force approach. The chitin? It does the whole thing in seawater at room temperature. It's a stunning example of nature's efficiency, creating a superior material with just a fraction of the energy and environmental cost.
The potential applications here are absolutely astounding, and this isn't science fiction. Scientists are already developing bio-inspired inks for 3D printing that mimic how the chitin does it. We're talking about incredibly durable coatings for tools, longer-lasting parts for airplanes and medical implants, and even new materials for soft robotics, all inspired by this little guy's teeth.
You know, the big takeaway here is that nature really is the ultimate innovator. The solutions to some of our most complex challenges, from making better materials to creating more sustainable manufacturing, they might not be waiting for us in some lab of the future. They might already exist, hidden in plain sight, in organisms we've been overlooking for centuries.
It really makes you wonder, doesn't it? What other geniuses out there, quietly grazing on a rock or floating in the deep ocean, holding the key to our next great technological leap? All we have to do is be curious enough to look.
Thanks for exploring the wonders of nature with us. If you enjoyed this journey, support BioVellum by liking, subscribing, and sharing. Let's explore the secrets of nature together.